This talk is on the real-time display with Gnuplot, and the targeted audience are those who are using general purpose languages such as C, C++, and the Fortran and some other general purpose languages that do not have graphical display functions built in. We're going to show in this talk how you can display your computational results while computing in almost real time with Gnuplot. Okay, so here's the outline of the talk. First, I'm going to briefly mention the needs, why we want to do this. Basically, we want to do a compute and visualize at the same time. And I'll mention a little bit about the workflow and the requirements for real-time display. And then I'll mention 3 approaches for computing and visualizing at the same time with examples. And in the end, I'll give a brief summary. So first, the needs. So sometimes let's say you experimenting some algorithms, new configurations, and some new ideas, new cases, and you want to see the results, and you don't want to wait until the end after the completion of the computation, and you want to see the intermediate results during the computation. Or you want to check the results and stop the computation if things go unexpectedly. Or another common use case is you want to debug your code by visualization. By visualizing the data, this is especially useful for physics and the mathematical problems. And for human, it is easy to visualize things, to see the air by visualizing the data and the shape rather than just looking at the numbers. For example, this is a one-dimensional a diffusion process. We're running a time evolution process. We're doing the computation, and this could involve many time steps. And during the computation, I want to see whether my solution looks right, and this is the solution is supposed to look like. So while the computation goes on, we expect to see this curve collapse down nicely and symmetrically. But however, sometimes we instead we see this. We see the solution blow up, and then we know something is going wrong. So we might want to just stop at some point and check our code. And another example, in a 2-dimensional physics problem, we have this very simple toy problem. This is a 2-dimensional diffusion process. The solution should look like this. While time goes on, the shape will gradually, smoothly collapse nicely. And if I want to solve this problem in parallel, and I would like to divide the domain into pieces, and then I use the MPI to solve the problem, and I solve the problem on individual domains separately. And then before I move on to the next time step, I need to have some communication to exchange data between those subdomains. Especially, I need to exchange data along the boundary. So in this case, I divide the domain into strips in just one direction into strips into, say, for example, 4 strips. And then we'll see if my MPI solution implementation is correct. So this is a serial implementation. And then let's look at the MPI implementation. This is the MPI implementation. I slow down the simulation. So because this is MPI, it involves the communication, and I want to see what's going on. Now, clearly, we see as time goes on, and we see some razor blades here. There are 2 bumps, like a blade, sticking up there. So apparently, this tells me that something goes wrong. So my MPI implementation must have some bugs that's causing the problem. The problem apparently is happening along the edge of the domain. And interestingly, this the weird phenomenon happened along this edge. If you can imagine, we divided this domain into 4 strips: 1, 2, and 3, 4. And there's only 2 along the 2 edges, 2 boundaries. We have this bump. So the solution at these points the solution doesn't change, and also it doesn't look symmetric. The problem itself is symmetric, but the phenomenon, the wrong solution doesn't look like a symmetric. So it tells me something really goes wrong. So for the MPI, this is one way of debugging your MPI implementation. For those of you, if you're using an MPI, it is not just a matter of speeding up the entire process, but also you need to make sure that the solution is correct. And quite often with MPI implementation, MPI or GPU implementation, any application that involves parallel processing and involves domain decomposition, there's a good chance that things can go wrong. There are a couple of ways of debugging the code. One is to use a debugger. One is the most commonly used approach is the use of fprint statements to print the data and examine the data. And the second is to use a debugger, a decent debugger, and it will examine the data, and hopefully you can find out what the bugs are. But as I mentioned, just by simply looking at the numbers, sometimes this is hard, and the human being is used to graphics, and visualizing the shapes or the graphs of the solution might be easier to see exactly where the problem happens. So for example, in this case here, by looking at the graph, I know immediately something's happening between the 2 subdomains. The solution is not right, and everywhere else looks fine, but not along the boundary. Okay, so that's just a couple of examples of the needs. Why do you want a real-time display during the computation? Now, next, let's take a look at the workflow and the requirements for real-time display. So there are 2 approaches for the display. One is what I call push, and the other is a pull. And the push, in the case of a push, the graphical program. So we need to have a graphical program to generate the graphs. So one, we have your application program. Your application program does the computation, and then we need a graphical program that generates the graphs. So in the case of a push, the graphical program is fed with the data stream from the application program. Okay, so in other words, the application program is pushing the data to the graphical program, and the graphical program is passively receiving data and generates the graphs. And the graphical program generates the plot synchronously. And sometimes calling a third-party tool directly from the application program. For example, pgplot. Pgplot is one of the commonly used plot program used by astrophysics and in some other disciplines as well. So calling a third-party tool directly from within application program belongs to this category. So inside your application, you need to add a call to call the library, call the function to plot. So this is a very common approach. So this is a push. So you push the data to the graphical program. And the other options, there's other options I will mention in this talk, includes using a pipe that is managed by the operating system. In the case of a pipe, you create a pipe. I'll mention the details in a few moments. You create a pipe, and your application program will pipe the output to the pipe, and the graphical program on the other end of the pipe will pick up, will receive the data stream and the plot, and generates the plot synchronously. Now, the second method is pull. In the case of a pull, the graphical program does not know when the data arrives. So the graphical program runs asynchronously in addition to side-by-side with the application program. So the graphical program needs to check periodically and to see if the data file has become available. And when the data is ready, it generates the plot. And this is the common way. Okay, so I mentioned there are two methods for graphical display during the computation for real-time display. And the expectation for real-time display, we want to have the display is platform independent. Okay, so we don't want to. It just works for Windows or works for Linux, but not the other. And the second, the display of the output should be smooth. That's the very natural expectation. And the third, we don't want to miss any missing frames or corrupted graphs. Again, that's natural requirement. And also, it's easy to implement, and the better just don't need to spend much effort. As the application programmer, you don't need to know much about the graphics. Graphical program, those special purpose graphical libraries, the less you need to learn, the better. Okay, so easy to implement, and hopefully we don't want to slow down the compute process, and this is a bit of hard. Any output during the computation will definitely slow down the process. Next, let's look at the computing and visualizing through a third-party graphics function. Okay, so this is case one, the solution. So in this case, on the left-hand side, we have the application program. The application from this is a flowchart from start to the end, and in the middle, suppose you have a time-dependent process. You have a time iteration it goes through from the first step until many steps in the future, and in the middle you have the output. You generate an output, and you want to plot and the output using a third-party program. In this case, XYZ plot doesn't exist. They just a third-party graphical program. Okay, so the application program in this case generates output and calls a function, the third-party function, to generate a plot. So here's an example, the PG plot. In this example of using a PG plot, this is a Fortran example. In order to use the PG plot, and PG plot is a package, and before the time step, the loop, you place a number of calls to a PG plot functions, routine subroutines, to initialize the library functions. In this case, I placed the 4 calls according to the documentation. I need to read the documentation, and to put the 4 calls before the computation start. That's the initialization, and then in the middle of the time iteration, I generate the solution. Solution here, X is the, for example, coordinates, and the Y here is U. Y is the solution. Okay. So first, I calculate the solution, and then come to this point. It's a time to generate the output, and if it is a time to output, so I want to generate output every so often. In this case, every, let's say, 100 steps. Every 100 steps, I generate an output and generate the plot. So this is the branch. If this is divided, if it divided by, say, 100, by 100 is is integer divisible, then it's a time to output the result. So I'm calling it 2 functions. Again, PG error and PG line. The PG line is the routine that generates the XY plot. Okay, this is example of using a third-party functions to generate data. Now, as you can see in this example, I would have to put these calls into my application in order to plot. And on the systems that these functions are not available, then my program won't be able to generate the plots. Okay. But fortunately, pgplot is a platform independent package, so it can be used for Windows and for Linux. But in general, if a third-party package is not platform independent, then your code is not portable. Okay. There's some other third-party packages, plotting packages for general-purpose languages, C, C++, and Fortran. If you Google it, and you will find a list of packages. If you Google with the keywords plotting packages, general-purpose languages, then something will pop up. Okay. And I think the PL plot is a newer version than the PG plot, and there are many other things. Python plot. This is an OpenGL library for modern Fortran, and the Gnuplot ISO stream interface for C, C++, and the Fortran, and so on and so forth. Okay, so this is an example of using a third-party function. You have to plant the third-party functions in your application program. So the workflow, the compute process produces the output and calls a third-party routine directly. And there's a pros and a cons. And the pros is it is synchronized. And the cons, the graphical display usually are tied to the language, not portable, and not so easy to customize. Does it meet the requirements that we listed? Yes, the graphical routine calls blocks, so it's able to read output from the main procedure, so there's no loss or corrupted data, and it can draw the plot within the same figure window, so it makes the animation of real-time in real time possible. So it meets the requirements. Now, second scenario, computing and visualizing through separate asynchronous processes. So in this case, the application program would generate the multiple files over time. Okay. For example, the program can generate 100,000 output files for later post-processing. And the later time or any time you run a graphical program and it runs through those files and to visualize the result. We can here's an example. In this example, I'm generating over 100 files during the computation because at different time steps, saving the solution to output 49, 50, 51, 52, and blah, blah, blah. So I'm generating a sequence of output files. And then later on, or at any time, I'm using a Gnuplot script to go through these files. So this is the Gnuplot script. Inside this script, I'm taking a number of output files from the command line. This is argument 1. This is this works for version 5 and above. It can take 1 to 9 up to 9 arguments. And inside the Gnuplot, I'm using a loop. A loop over from 1 to the number of output. And then inside this loop, I'm plotting the solution. And I'm using the file with the file name. Each file name has a number. And then after I generate the plot, I pause for a bit. No, I just pause to wait for, if I put the -1, which means it will pause indefinitely until I hit enter. Otherwise, we'll pause whatever the number. You put 1, it will pause for 1 second, and 2 seconds, or 10 for 10 seconds, and so on and so forth. And from the command line, I simply just run this Gnuplot command, the name of the script, and the 20, that's a 200. 200 is the number of files I generated, for example. Okay, so let me just show you the example. Let me go to the folder. Let me just generate the example. I wanna go. Okay, 1,000 time steps, and every 10 steps. So that will be in total. I will have 100 output files. Okay, and then I'm simply just going to run the simulation. Run the simulation. Okay, so I have generated 100 output files. 100 output files from output. So if I do output, that's 100, 101, including 0. And then the next I'm going to run the Gnuplot. And what is the snapshot, I think? To check which one. Is this one? No, not this one. Yeah, this is the one. This is the one that has the for loop. Let's take a look at, actually. It's a good idea to take a look at this file. This file, this is a GNU plot script. And these lines defines the setting to generate the plot. It is interesting to know near the end, number of output files is set from the command line by the command line argument, the first argument. And then we're using a for loop, we're using a do loop, the loop over from 1 to the number of output files. And the inside this loop, I'm generating two-dimensional, a 3D mesh. Okay, so I'm going to run this script with the option -C so that it can take the script, and also the argument. An argument is 100. Okay, 100. So it will display this one at a time. So just keep hitting. Let me just make it a little smaller so you can see it. So this way you can see the change of the solution. Okay. Let me just go back. So back here, I just showed how to visualize the files generated, many files generated afterwards. Okay. Now some comments. So the workflow. This is the most common approach. We generate a bunch of files, and then we use another completely separate graphical process to visualize the solution. The compute process produces the snapshots of output periodically and stores them into a sequence of files. And we use a separate process to view the results in sequence with some delay. Now, there are pros and the cons. The pros, no change in the compute program. So the compute program is completely separate from the graphical display. So you can keep your, you don't make any changes to your program, but just make sure that your output matches the format that can be read by a Gnuplot. Okay, and the program knows nothing about graphical display. And then the cons, many files might need to be saved. Okay, so if you're, what if you're gonna you want to generate thousands of files, 5,000 of files? That is not practical, and especially on our systems, then we're not recommending users to generate too many files within a single directory. And this is also true on your own personal computers. You don't want to put too many files within a single directory. That will slow down significantly the performance of your file system. Okay, so that's not practical. Does it meet the requirements? Yes. The graphical program reads the data from each the file, and it generates each one frame for the entire for the display for the display of the solution over time. The graphical program can generate multiple frames within the same figure window. So again, It makes the animation in real time possible. Okay. So next, similar to the previous one, but in this case, instead of generating many files with a number going from a 0 to 1,000, I only generated one file, and this file will be read by the graphical program over and over again. And this file, of course, will be overwritten. Suppose that there's enough time between the file that was generated and that the graphical program can read it, then we are able to see the sequence of images. Okay. For example, let's take a look at example. So how does it work? So inside the application program, instead of generating a sequence of output, I'm just only generating one output file called out data, and this will be overwritten over time, of course. And then the Gnuplot, I'm using a Gnuplot script, and this time the Gnuplot script is very simple. It reads the file output.data and generate splot. The command on the from the command line, I'm using a pipe. So I'm running the application program first, and then pipe to a Gnuplot. The Gnuplot takes this script, reads the script, runs the script. The option persist is to require the Gnuplot to generate a figure window, another figure window to make sure that figure window will stay, so that we only have one window, one graphic instead of multiples, so that we can see the animation inside that window. Now, keep in mind on Unix system, if you're running two commands side by side on each side of the pipe, the vertical bar is the pipe. Here, heat C is the first command, and the Gnuplot is the second command. It doesn't mean that the first program will run first, and then the second command will run. It means instead, it means both processes will be invoked, will be started and running concurrently. The pipe acts like a bridge so that the output from the first command, first of the process, gets pushed through to the second process. The second process, therefore, can read the input from the output from the first process. Okay, so these two processes are completely separate. The application program knows nothing about the Gnuplot, and the Gnuplot knows nothing about the application program. The only connection in between is through the pipe. The data is coming from the application program, and in this case, the data actually is not directly going into Gnuplot, but the Gnuplot is using this file output date as an input to generate the plot. And as we can see, there might be problems. Let me see if I can. Okay, let me need to kill. Okay, so I'm still using this input file, and then I'm running C. Okay, now I'm running this application program, and then I pipe to the Gnuplot and running Gnuplot, and with an option persist so that I only have one window, and the plot. And as you can see, I need to kill this. Oops. Kill this window, run again. It sort of works, but I got some corrupted the frame and try it again. You see? And then try it again. Okay, so this time it's better. But as you can see, I have failed twice. So this approach is not reliable. This is not reliable because it's not synchronized. Oops, where's my presentation? And this is because this file output data gets overwritten. So when the Gnuplot reads this file, go back. When the Gnuplot reads this file, that file could be truncated to 0 to be written by the application program because they are not synchronized. The Gnuplot there's a hit and miss. It doesn't. The Gnuplot does not necessarily always get a complete good set of data. Okay, so this is not reliable. However, if the application program, let me just show you that example. This is an example. Let me start this. So I am displaying the what's going on the cluster. This the usage, number of cores running in green, and number of cores waiting in the queue. So I'm pulling data. I have one application. The one application is pulling data, and save it into the same file. And then I'm running in the Gnuplot. The Gnuplot is reading that file and it generates the Gnuplot is generating this plot and updates this plot. I'm updating the data every 5 minutes. Okay, so it gives the Gnuplot enough time to read the data. So within that 5 minutes, that file won't get updated. So therefore, I would not, in this case, I would not get corrupted data. Okay, but if the application program is frequently updating the output too fast, such that the Gnuplot cannot keep up, then now you'll end up with partial display or corrupted corrupted graphs. Now, in order to display the graph, this graph we're seeing, as I mentioned, I have one process is sampling the data every 5 minutes or so. And the Gnuplot is checking. You see the Gnuplot, it updates the graph. The Gnuplot will read the updated data file. Now, this is the logic that we should have. So from the start, first, we need to check whether the data exists or not. If not, we're going to go back and better put some sleep. Okay, here's again, it updates the plot. Oops. If the data exists, and then we come to the next stage, we get the file, get the timestamp of the file. If the timestamp of this file is greater than the previous timestamp, which means the file is being updated, then I'm going to go plot the data. Okay, and otherwise, I'm going to go back here and sleep. Okay, so that's the logic. Okay, so we need to have this a little smart logic built in so that the Gnuplot will not be in a busy wait. So here's what we do in the Gnuplot script. We get a timestamp from the system, and then compare the time, whether compare the timestamps. If it is new, then if it is not new, then we pause, sleep for 30 seconds, and reread. This reread will force the Gnuplot to go back. Okay, this is a loop. It facilitates the repeat process. Reread will go back. If the timestamp is newer, then we go plot. This is what we see here. The graphs is updated. And then after the plot is generated, and this reread will put the Gnuplot back to the beginning. So the key here is the reread in the Gnuplot. The reread will make a Gnuplot to go back to the beginning, so that we will have a loop so that we can make use of we can use that to check the data and to reread the data, generate the plot. So it is possible that we're using the same file name to generate the different plots when the same file gets updated. Okay, and the shell command on from the command line, I simply just type Gnuplot, and I'm just running this Gnuplot. Okay, running this Gnuplot. Remember, this Gnuplot, the plotting plot generating process is separate from the application, so I can run this Gnuplot separately. Okay. Summary here. Okay, I need the. Oops. Close this. So summary here, the compute process produces snapshots output at a given time, but only one output file. Okay. The pros and the cons, and no change in the operating in the compute program, and display control is done separately. And the cons, the compute program and the graphical program run concurrently, and they're not synchronized. The compute program can update it, the output file while the Gnuplot is reading file. So we're running into a race condition. Does it meet the requirements? Yes, we see the plot. So next, the better solution, the third scenario, the computing and visualizing synchronized through a pipe. So how are we going to do that? In the application, we pump the output to a pipe. And then the graphical program picks the data, receives the data from the data stream inside the pipe, and generate the it generates the graphics. And let's see how it works. So here on the left-hand side, this is application form, application program. In the application program, all we need is to create inside the application, create a pipe. Create a pipe and forks a Gnuplot process. It does two things. One, it creates a pipe. It creates a pipe, and then it forks a Gnuplot process through the pipe. Okay. And the second, we have the application program to read the configuration, to read the Gnuplot script. Again, the application program doesn't need to know the Gnuplot script. It just reads in the script, okay? Those are settings for the plot. And then in the middle, in the time evolution iteration process, when the time at the time to generate the output, we generate two things. One is we write the plotter command to the pipe, and then we write the output, same format, coordinates x and y and the solution, to the pipe. Instead of writing that to the file, now I'm writing to the pipe. And from the command line, we simply just run this application. There's no need to run the Gnuplot because the Gnuplot is being launched, forked inside from this application. And this diagram shows what's happening. So this is the application. The application creates the pipe. And it generates a sequence of data. This is a data stream. The first thing to write to the Gnuplot, to send the Gnuplot, is it reads the configuration file from disk file and it writes it to the pipe. So the first chunk of data stream contains the Gnuplot setup commands. And the second is the plot command, splot, followed by a set of data. And then the next splot data. And so on and so forth. So we have this data stream in the pipe, okay? And this way, the Gnuplot here, the Gnuplot on the other end is receiving data synchronously from the pipe. So it can generate the data smoothly. Let me just go back to the simulation. Let's see how we can run it smoothly. We're using more steps. And then we're going to run. See which one is which. Okay, so we we want to run this one. We want to run with the Gnuplot. So now this time, we see a very smooth real-time display while computing. Okay, this is the third approach. Let's go back here. Oh, I need to kill. Stop the process. Okay, so let's take a look at this this approach. The compute process produces snapshots, the output at a time periodically, and then a separate GNU process reads the output from the pipe. The pros and the cons. Pros: the compute and display are synchronized, and the graphical display is smooth. The data stream in the pipe is handled by the operating system. Cons: the application program needs to open the pipe and close the pipe through a system call, which might not be explicitly supported, for example, in Fortran. But that's it. That's the only thing you need to do. Okay, so again, this is the in my view, this is the best approach. Finally, a summary. We mentioned the three approaches. One is direct, and the second is the asynchronous separate processes, and the third, which I believe that's the best, the synchronized through a pipe. I just put up the summary here, and I should stop here and take some questions that I might have from an audience.